This brief tutorial will show how to perform seismic analyses using different mass sources. In most structural analysis, the assumption that masses do not vary is appropriate. However, on occasion it may be necessary to perform analyses where the masses vary, such as in structures that support changing equipment or piping loads. For this tutorial, we have created a simple brace frame which is used to support a vessel that varies in weight and thus mass. SAP2000 allows several different ways to define the mass in a model. Mass sources are set using the define mass source command. A default mass source is always defined. And if we click the Modify Show button, we see that the default is set to use the element self mass along with any additional mass that may have been assigned. We will develop two additional mass source definitions that will use specified load patterns, one where the vessel is empty and another where the vessel is full. But before we can do this, we need to define the load patterns for the vessel. To do this, we leave the mass source definition and go to the Define Load Patterns command. In addition to the self-weight load case, we will add two load patterns. The first will be named Equipment Empty, with the type of other, the second will be named Equipment Full. We will also define two load patterns for static seismic load patterns. The first will be called Quake Empty, with a type of quake and an auto lateral load pattern of IBC 2006. This will generate a static seismic load. The second load pattern will be named Quake Full. Even though these last two load patterns look the same, we will be using two different mass sources when running the load cases, and thus must have two different load patterns. Now we will assign loads to represent the empty and full conditions of the vessel. We will assign the empty weight of the vessel to the top beams. We will assign an arbitrary distributed load of 1 kip per inch in the gravity direction. Reselecting the two top beams, we will now assign the load of the vessel when full. Here we will use 2 kips per inch in the gravity direction. Now we can return to the mass source definition. On the mass source form, we click the Add New Mass Source button. We will name this new mass source Vessel Empty. In addition to the element mass, we will add mass from the equipment load patterns. For this mass source, we will use the Equipment Empty load pattern. We will add one more mass source named vessel full. Again, we will include element self-mass and a load pattern, this time the equipment full load pattern. Next, we move on to defining the load cases. On the Define Load Cases form, we see that load cases have automatically been created for the load patterns defined. The two load cases that we are most interested in are the Quake Empty and the Quake Full cases. Selecting Quake Empty and clicking on the Modify Show button, we can see the parameters for this load case. In the lower right-hand corner is the mass source for this load case. Note that it is set to the default mass source, and also note that it cannot be edited. It is grayed out. The mass source drop-down list is available in only 3 types of load cases: nonlinear static, nonlinear stage construction, or nonlinear direct integration time history. However, there is a way to use a different mass source without changing our defined load cases to nonlinear. We can do this by adding a new load case for the sole purpose of changing the mass source. Clicking the Add New Load Case button, we will name the case nonlin static empty with an analysis type of nonlinear. Note that the mass source drop-down list is now available. For the mass source, we select vessel empty. We will leave the load applied section blank, although we could apply loads if we were including P delta. We then click OK to close the form and click Yes. Now we highlight the Quake Empty case, and again click the Modify Show button. Note that the default mass source is still showing. This time we will modify the load case by selecting the Stiffness at End of Nonlinear Case option and selecting the Nonlin Static Empty case. Note that the mass source now changes to the Vessel Empty source. Thus, our Quake Empty load case will now use the mass associated with the empty vessel. And because the Nonlin Static Empty has no loads associated with it, the stiffness from this case is exactly the same as the linear stiffness. Thus, the net result is that the Quake Empty is a linear load case simply using a mass other than the default. We will use a similar approach for the Quake Full case. We start by defining a new load case, nonlin static full. Again, we select a type of static nonlinear, and this time set the mass source to vessel full. Again, no loads are applied. Now, highlighting the Quake Full case, we click the Modify Show button and select the Nonlin Static Full case as the stiffness. Note that the mass source has switched to vessel full as desired. We can now run the analyses. With the analysis complete, we will now review the results for our two static seismic load cases. First, we will display the deformed shapes. For the load case where the vessel is empty, note that the lateral displacement is approximately 0.18 inches. If we switch to the case where the vessel is full, note that the lateral displacement is now more than 0.34 inches, nearly double that of the case where the vessel was empty, which is as expected due to the significant increase in mass. Next, we will look at the forces for the two seismic cases. For the vessel empty case, the axial force in the top race is almost 21 kips. While for the vessel full case, the axial force jumps to over 40 kips, again as expected. Now we will show how the mass source may be varied when doing a linear elastic time history analysis. We start by unlocking the model so that we may make changes. Next, we will define a time history function. Here we will create a simple cosine record, but we could use any recorded earthquake file. Next, we return to the define load cases command. Highlighting the modal case, we click the Modify Show button. We are going to change the name to modal empty to represent the modal data for the empty vessel. We will leave the type of mode set to eigenvectors and the number of modes set to 12. We will, however, change the stiffness to use option and select the non-lin static empty case. Note that the mass source switches to vessel empty. With the modal empty case highlighted, click the Add Copy button. We will change the name to modal full, as this will create the modes associated with the full vessel. The only other changes we make are to switch the stiffness to non-lin static full. Again, note that the mass source changes. Next, highlight the quake empty load case, and we will change this to be a time history analysis from a static analysis. Select time history from the drop-down list, along with a solution type of modal. For the modal load case, select modal empty. And revise the loads to be the acceleration from our earthquake record. We will do a similar revision to the quake full case. Except that we will use the modal full mode case. As a last step, we will set the analysis to planar. Now we can rerun the analysis. Displaying the deformed shape for the time history analysis with the empty vessel. We see that the lateral displacement is about 0.34. For the time history analysis with the vessel full, the displacement is about 0.40. Likewise, when looking at axial forces, we see a force of about 36 kips at the top brace for the empty vessel case. And a force of about 41 kips for the full vessel case. Thus, we have obtained time history analysis output for two different arrangements of mass. As a side note, the ratios between the full and empty cases for the time history analysis are not as large as what we saw for the static seismic cases, which is not unexpected. In a time history analysis, the mass also impacts the periods of the structure, which affects how it responds to the frequency content of the input record. This concludes this tutorial on varying masses for seismic analysis.